Hello everyone and welcome. My name is Eric Coleman with IIST and I will be the moderator for today's webinar, Improve Lifecycle SQA with Measurements by Alfred Sorkowitz. We're excited you're able to join us today and set aside an hour to attend this webinar. This webinar is one in a series of free webinars to introduce the topics as well as the presenters of the upcoming SQTM conference in San Diego, California, September 13th through the 18th at the Sheraton San Diego Hotel and Marina. The conference focuses on advancing the test management and quality management professions by providing practical methods based on best practices. The ongoing theme of the conference, Practical, Proven, Feasible, keeps the focus on what works. To view the conference program and more information, visit www.qualitymanagementconference.com. Be sure to join us for the next webinar in the series, A Disciplined Agile Test Design Process by Dr. Meg DeHanna on April 27th from 11 a.m. to 12 p.m. Central Standard Time. To learn more about this and other webinars in the series, go to www.qualitymanagementconference.com. This webinar is being recorded and will be made available for viewing within 48 hours at www.qualitymanagementconference.com. I will now turn the webinar over to today's presenter, Al Sorkowitz. Al?
Al Sorkowitz, welcome to this webinar. Topics we're going to be talking about are the rationale and purpose of SQA, spending a whole lot of time on using measurements, using measurement data to set new SQA goals. Some measurements we're going to be talking about are software size measurement, software staffing measurement, and then we're going to be talking about measurements that can be used in the requirement and design phase of the software lifecycle. And then, if we have time, we'll be talking some measurements that could be used in the unit testing progress measurements. As far as the rationale for software SQA, the realization that software quality cannot be added, inspected, or tested in after the software has been developed. It has to be built in at every phase of the life cycle. So you have to build in quality in the requirements phase, the design phase, the unit test, code and test phase. All of these phases have to have quality, and it's too late afterwards. Software quality assurance, the purpose. SQA involves reviewing and auditing the software product and activities, and again throughout the software lifecycle, to verify that they comply with applicable procedures and standards, and providing the software project with other appropriate managers with the results of these reviews. And again, we're going to be talking about measurements, and when I talk about measurements, I really mean measurements and analysis. And then, of course, the question is, why measure? Because without measurements, you only have opinions. Why analyze? Because the data you collect can't help you if you don't understand it or use it to shape your decisions. The purpose of measurement analysis is to develop and sustain a measurement capability that is used to support management's information needs. And we're going to talk about software measurements, and what I'm saying is measurements gives you visibility into the software development process. Are we on schedule? Are we meeting any productivity or quality goals? And I'm going to make the case, and see if you buy it later on, that measurements gives you early detection of potential problems, and if you detect problems early enough, in time to take actions. If you don't detect the problems until the end, then it's too late to take any actions. Trends uncovered can be projected to evaluate potential impacts. Let's go over this chart. This is capturing and using metrics data to set new software quality assurance goals. And this is data from Siemens Corporation, a German corporation, one of the largest engineering companies in the world, with over 60,000 people in America. And as for the columns, we're going to be talking about the life cycle phases: requirements, design, code, and we're going to talk about system test and field use as operations. Now the first row is fault origination. In which phase of the life cycle was the fault put in? The second column is fault detection. In which phase of the life cycle was the fault detected? So we can have where the fault was put in and which phase of the life cycle the fault was found and fixed. And on the bottom we have cost per fault. Depending on where in the life cycle you find it, there's a different cost. So let's go over the Siemens data. And by the way, Siemens was always recognized as one of the leading companies in developing software. And every time you went to a conference, people would talk about Siemens. So let's take a look at Siemens data. Siemens data said that 10% of all the faults were put in the requirements phase. Yet when they left the requirements phase, they only found 3%. So now we're left with having some requirements fault when we go into the design phase. Now Siemens data shows that when you find a fault in the requirement phase, it only costs 1 kdm. Now K is 1,000 and DM is Deutschmarks. The study was conducted in the beginning before Germany went to the euro, so they kept it in Deutschmarks. So Siemens data shows that if they find a fault in requirements, it only costs 1,000 Deutschmarks to find and fix the fault. So now let's take a look at the design phase, and we know we have some requirement faults that haven't been found. Siemens data shows that 40% of the faults originated in the design phase. And Siemens data shows that when they left the design phase to coding phase, they only found 5%. So now when we go into the coding phase, we have some requirement faults, some design faults. And Siemens data shows that if you find a fault in the design phase, it again costs 1,000 Deutschmarks to find and fix it. Again, Siemens data shows that 50% of the faults were originated in the coding phase. Yet when they left the coding phase, they only found 7%. So now we're going to go into system test with requirement faults, design faults, coding faults. Siemens data shows if you find a fault in the coding phase and fix it, it costs 1,000 Deutschmarks. Let's, as an example, switch to system test. Siemens data shows that 50% of all their faults were found in the system test phase. But the problem is, if you find a fault in the system test phase, it now costs 12,000 Deutschmarks to find and fix it. So finding in the system test phase is 12 times more expensive than finding it in the coding phase, 12 times more expensive than finding design phase, and 12 times more expensive than finding it in the requirements phase. So what we're saying, it'd be cheaper if we found our faults earlier. Now let's go to the field use, which is operations. And Siemens found that throughout the life of the application, 10% of all the faults were found in the field use, in operations. And data shows that if you find a fault in the field, operational, it costs 20,000 Deutschmarks. So here you're finding it costs 20,000 Deutschmarks a pop, and in the system test it costs 12,000. The whole trend in modern programming practices is how do we structure our process so that we can spend more effort in the earlier phases where it's cheaper to find and fix errors. So again, let me just say that, by the way, let me just remind you, Siemens has this data. And Siemens was shocked to find that 50% of the errors were in system test at 12K a pop, and 10% of the errors were found in the field at 20K a pop. Siemens was surprised at this and set a new SQA goal that there would only, to try to set the goal that 10% would be found here and 5% would be found in the field. So how do you do that? You don't just send out a memo saying you only found 10% in the system. It went to the software process improvement group and said, what more could we do in requirements phase? Do we have reviews? Do we have walkthroughs? What more could we do here? We'd like to spend more time and money here because if we find that it only costs 1K a pop rather than 12K a pop or 20K a pop. But the point is, Siemens has the data to show this. Let me ask you a question. How many of you belong to organizations that have this data? If you don't have this metric data, you really have no idea how you're doing. So you don't have any idea if you're doing well or poorly. And you don't have any idea, as an example, that Siemens had to know that in system tests they were finding 50% of the error. And they found that unacceptable to be paying 12K a pop and 20K a pop, when if they found ways to spend just a little more effort here and here, it would be extremely cost effective. And by the way, another problem with not having the data, as an example, if you're in the independent system test team and you don't know how many errors are you finding, if you're finding 50% of the errors, how does that impact the goal and schedule you set for system test? As an example, finding 50% of the errors entails a lot of rework. So if you're not aware of this historical data, it may seem that all your budget and schedule for system test didn't take into account 50% that leads to a whole lot of rework. So again, without this data that Siemens has, you really have no idea how you're doing. You have no idea how your SQA life process is doing. So let's go on. One of the first metrics I'm going to be talking about is software size. How large is it? And let's take a look. These are the official IEEE names, so you don't have to do it. Let's say these things are in the very beginning when you're analyzing the problem. This is when you have the software requirements. This is where you have the preliminary design, and this is when you have your detailed design. And as an example, in the very beginning, you have an estimate that it's going to be about 120,000 lines of code. This is your best estimate, and in the beginning you have to have some estimate to know the schedule and cost. So let's say your original estimate is something, again it's only an estimate, is something in the line of 120,000 lines of code. Now once you have the software spec completed, the software requirements, then you have to make another estimate and saying, with all that I learned from the software requirements, I now think it's going to take 160K of words. Because once you have the software requirements, you have all the details on what you have to design, code, and test. And let's say in the preliminary design review, you find nothing different. But when you get to the detailed design, the critical design review, the detailed design review, you found some other things you needed. So now, again, your best estimate is 180,000 lines. Don't forget you haven't coded yet, so you don't know. But what you're saying is these are the best estimates. And what you're seeing is the size is increasing. And you haven't even started coding, and you're now X% between original 120,000 lines and 180K lines. Obviously, it's going to cost more to code, document, and test 180,000 lines than 120,000 lines. So the software size has an impact on your schedule and cost. And let's take a look. This is the software size metric. It tracks the change in software size. And why are we worried about something as simple and as easy as software size? Because software size is a major variable used to estimate development effort and schedule. Barry Bain, in his book Software Economics, says size is the major driver of cost and schedule. Let me repeat this. Barry Bain, in his book Software Economics, says that software size is the major driver of cost and schedule. So as the size gets larger, it's bound to have an impact. And again, unplanned increases can adversely affect schedule and cost. So that's the reason for keeping this very, very simple metric called size. Again, we all understand software creep can be related to requirement creep. Software undersizing has been a problem due to optimistic estimates. And again, if you haven't, like Siemens, been capturing historical data, there's usually a lack of historical data on size growth and an incomplete understanding of requirements. So again, software size is a very simple to understand metrics. All of them are simple. It doesn't measure anything else. It doesn't give you any insight in anything else but the growth in size. And that's important because size is the major driver of cost and schedule. And again, this would be in a metrics plan, corrective action. This is the metrics plan of one organization. An increase over 5% in the size per reporting or over 20% between phases require a cost schedule impact. What this company is saying, if the software size increases a certain amount, then we have to stop and evaluate the impact of the increased size and what we have a cost and schedule impact. And the impact can say there is no impact, or yes, there is a sizable impact, and we may have to adjust our cost and schedule. Analysis. Software size should not exceed thresholds without an understanding of the reason. You have to know what the reason is, why the size estimates are increasing. And again, change in software size often results from a better understanding of the software, the detailed software requirements, which you may not have been aware of when you started the project, with just some high-level requirements. Now, let's take another look at another simple metric, software personnel staffing. Again, like software size, it's one simple measurement. It only measures personnel staffing. It doesn't have any impact. And by the way, each of these measurements are very simple. but when we put a dozen of them together, we can get a well-rounded picture of what's going on. And again, this is a little in error. It's not 300, it's 30, 40, 50. And here is time. And what we're doing now is what we're going to do very often in the different measurements. Right at the beginning, when we have our software size, we say this is our planned estimate of size. We're going to start off with 20 people, and in May we're going to go up to 30, and in August we're going to go up to 35. So this is our software staffing plan. This is what we do when we start the project. When we want to figure out cost and schedule, we have to know what is the staffing plan. So again, in the beginning, this would be figured out. This is a staffing plan to complete the software job on cost and schedule. And then every reporting period, here it's every month, we put in the actuals. So again, the way we're going to set this metric up is the relationship between planned and actuals. So in February, we said we would go up to 20, went up to 19, pretty good. In March, we said we're going to go to 22, we're still at 20, not too bad. In April, we're going to go, we said we'd still be at 22, we're at 19 or 20. So we're still pretty much, but notice what happens. In May, we plan to go to 30, and we're still at 19. So now there's a difference in staffing between 30 and 19. In June, we were supposed to stay at 30, and we went up to about 22. Still that difference between planned and actuals. In July, we were supposed to go up to 35, and we're now at about 23. So now again, we have the difference between planned and actuals, and this thing stays the same. What this tells us is we never met our staffing plan, so intuitively, how could we do what we said we're going to do if we never met the initial staffing plan? So again, this is a very simple metrics, and it gives us insight into the staffing. And what will be happening as an example, if the software size in the previous measurement went up and the software personnel, we didn't meet our staffing, we can see just by looking at these two measurements that we certainly have a potential problem in finishing our job as planned on budget and schedule. Again, software personnel staffing metric. It does not, each measurement, by the way, does only one simple little thing. It tracks the ability to maintain planned staffing levels. Again, corrective action. This organization said changes of 20% against planned and actuals require a cost schedule impact. If there's a change in staffing by 20%, then you have to stop and go back and do a cost schedule impact. And either you can say there is no impact, or more likely, you have to revise the staffing plan and the budget and schedule. Now, as an example, you can tailor this. You can report staffing separately for senior people, or you can report staffing for the testing team, or you can report staffing for the whole project. So again, this measurement, the software staffing metric, tracks ability to maintain staffing levels. Let's talk, next we're going to talk about some measurements that we're going to use in the requirements phase. But let's go over something about the requirements phase. And this is an example that was surprising to me. It's data from Lockheed Martin. And it shows you how the requirements are changing. This is the percent of specification requirements involving software. So when we have a new system, and this is Lockheed Martin's over many generations of their fighter planes. In the 60s is the F-4. Each one of these is the latest generation of American fighter planes, the U.S. Air Force planes, the A-7, the F-11, in the 70s the F-15, in the 90s the B-2 bomber, in the 2000s the F-22, and now Lockheed Martin is developing the F-35. Let's take an example of the 1960s and the 2000s. In the 1960s, Lockheed Martin says, of all the requirement specs for building this plane, which includes all the hardware requirements and all the software requirements, software requirements were less than 8% of all the requirements. 92% of the requirements to build that airplane were hardware requirements. And that seems normal. To build this plane, how fast must it be? How big should the wings be? How powerful should the motors be? All the things to build the most modern jet, Air Force jet in the world. 92% were hardware, and approximately maybe 8% were software specs. And by the way, to do those 8% software specs, Lockheed Martin said 1,000 software lines of code. So the hardware was 92%, the software was 8%, and the implementation was 1,000 software lines of code. Let's take a look at the year 2000 with the jet, the F-22, and Lockheed Martin says that 80% of the requirement spec was software and only 20% was hardware. To drive that plane, there was so much complexity that you needed so much software requirements to give the operators and the maintenance people choices and options that had to be resolved in software. So you had 80% software requirements and only 20% hardware requirements to build that plane. And by the way, Lockheed Martin said it took 1.7 million lines of code to build all those software requirements. So we went from 1K to 1.7 million, and in the mid-70s, the software requirements were about 38%, and it took 50K lines of code. So we went from 1,000 lines of code to respond to the software requirements of the F-14, and there were 80% software requirements, and it took 1.7 million lines of code. And now, Lockheed Martin is estimating that the F-35 will take 6 million lines of code, and that's a hell of a lot of requirements to have to implement in software. So what we're saying is software requirements are getting larger and larger, and it's getting more and more difficult to keep track of them, and it costs more and more lines of code, of course, to implement more requirements. So let's talk about a software measurement that's called software volatility or requirements volatility, or some people call them requirement stability. How stable are your requirements? And we all know requirements somehow tend to grow. And when requirements grow, of course, software size tends to grow. So let's talk about, again, when you initially started the project, you had to have some idea of how big it was going to be. And the estimate was we were going to have about 1,500 requirements. That gave us some sort of idea together with size, so that we could make some estimates on budget and schedule. When we did the software review, the software spec review, or the software requirements, we found out things we weren't aware of, and we now found out that the estimates, well, we have the requirements, that we now have, as an example, 1,700 individual requirements. And in developing the new kinds of way we do requirements, we want to document individual requirements, because we will have to keep track of the requirements to see that each of these individual requirements is uniquely tested. So we now know from this requirement spec that there are 1,700 requirements. And when we did the preliminary design review or the high-level design review, we found out more things. We need more modules. So we now understand we have 1,750. And when we did the critical design review or the detailed design review, we're now up to 1,800 individual requirements. So the requirements haven't been stable, and this is even before we coded the first word. Of course, any change in requirements after a coding are even more serious than the changes during high-level design and critical design. So here we're seeing the requirements have been highly volatile. They haven't been very stable. And if the requirements are increasing, the size is probably increasing. So that has a major impact on budget and schedule. And what this measurement does is gives us insight into the stability. It doesn't give us insight into anything else. But if we start looking at software requirements and software staffing and software size, if the size is going up, if the staffing wasn't met, the requirements are going up, we have a pretty good indication early in the game that we're going to have potential problems. And we could have seen that we're going to have potential problems as early as when we finished the software requirements. When we finished the software requirements and saw that our initial estimate was so off, we should have had an idea that this is going to have an impact on size, it's going to have an impact on code, it's going to have an impact on test, it's going to have an impact on documentation. Again, another way we put a metric on requirements is not system stability, but requirement changes, total changes. How many changes are there? Here we saw, as an example, in month 1 there was this many changes, and this is what was happening. When we got to month 4, the changes were increasing, and at some point, hopefully once we made all the changes in the requirements were getting less and less. Again, these changes have an impact. And this requirement stability or requirement volatility, when we looked at that, gives us an idea of the impact. Again, once we keep track of requirements, this is an analysis of requirement errors, so we can learn if we're doing anything special wrong continually, so we could change our process for requirements. And here we're talking about class of errors. And NASA, in one of the documents said that the largest number of requirement errors are ambiguous requirements. Here are a number of ambiguous requirements. Here are a number of incomplete requirements. Here are a number of incorrect requirements. Here are a number of untraceable requirements. and here are a number of inconstant requirements. So again, we can see that we have a whole lot of ambiguous requirements, and so we know next time in reviewing requirements, we have something to be aware of. So now let's take a look at software volatility metrics or software stability metrics. Again, it tracks the stability of the software requirements. Doesn't do anything else, but when you take a look at this in combination with the other measurements, you can see that there could be a potential problem. So it tracks the stability of the software requirements. And by the way, something very similar could, and we'll talk about it, can also track design stability. How stable our design, just as unstable requirements can have a potential problem, unstable design can also have a problem, which means we have to throw away design and stuff like that. And if the requirements or design that's stable can serve as a predictor of cost increases and rework. Rework is a major problem with cost increase. If the requirements aren't stable and the design aren't stable, all the changes can lead to rework, which is a costly process. For each of the system or subsystems, the metric can track the growth in the number of requirements. As we do the software requirements, we now have a better idea, and a number of requirement changes. And a requirement is considered change. It has been modified or deleted or a new requirements. Again, modified requirements or new requirements can lead to potential rework, which is costly. So again, the volatility metric or stability metric gives us an idea of the stability and design and the potential problems. Corrective action, against, this is one organization saying that a 10% change between requirements design requires a cost schedule impact. Again, it's a potential danger, so we want a cost schedule impact to see what is the impact of these requirement changes on the schedule and cost. And this organization says any requirement change, any change after coding starts requires an impact statement. It's potentially because when you have coding, any change when coding starts, you may have to throw away large amounts of code, you may have to throw away large amounts of test data, you may have to throw away and redesign the program, you have to throw away requirements. And what analysis? Requirement growth and stability should be tracked throughout the project, usually by the configuration management people. Traditionally, requirement changes we have early in the phases. Changes after design completion can have a significant impact. So again, the metric could tell us very early about the potential problems, and if we know about a problem early enough, we could make some changes, or we may be able to make some changes. Let's talk about design progress, how we're making progress in the design phase. And again, the red is planned, the green is actual, and the yellow is plan 2. So here in the very beginning, the design team says, in this large software system. There's 8. The initial estimate was 800 designs, unique designs of the different modules and procs and programs. And this was the initial planned schedule. In February, they would completely finish 200 designs. In March, they would finish 350 designs. In April, there would be 600 designs, and they would be finished all 800 designs in May. And this is on a monthly basis, and whatever your review period is, weekly, bi-weekly, or monthly, you put in the actuals. So in January, they should have completed 150. They only completed 100. In February, they should have completed, the plan was to complete 200, and they actually did complete 200, right on the ball. In March, the schedule was to successfully complete 350 designs, and they only did a little more than, well, they did about 250. So in March, they were 150 designs short of their schedule. This was enough to cause a cost impact, and in reviewing their productivity and their ability to finish successfully designs, they decided that there is no way they could meet that, and so they came up with Plan 2. They're saying what the best estimate now, given what we've learned about how our productivity is we cannot finish 800 by May. We can finish 800 by June. So Plan 2 says in April we're going to have 400. In May we're going to have 600. And in June we're going to have 800. So right now we know by Plan 2 that we can't meet the May schedule. The only schedule, if nothing changes, we can meet the June schedule. However, since we found out early about it here, what can we do? Well, we now know early enough that we can make some impacts. One is what if we could increase the staffing? Well, if we could increase the staffing, maybe we can meet that. Another option we may have is we may cut down on some requirements so that we don't need 800 designs. We may only need 600 designs. Again, we have some options. We can cut down requirements and say, we'll do these in the next phase, or maybe we can add staffing. But if, in looking at the impact, and it's agreed that there is no more staffing available, and we can't make cut any commitments or requirements, then the best we can do now is June with a one-month slippage and a budget slippage. So what I'm saying is the design progress measurement gives us impact in a potential problem early enough. And in this case, in March, we knew that we were 100 completions of design behind, and we had a cost impact. And we said if we can't make any changes, this is the best we think we can do. If we can make changes, we have impacts, and so we'll still come up with a different plan too. So again, here we have the initial plan. Here we have the actuals. And here we have Plan 2. Now let's go on. Here we said we were in March. We couldn't meet the schedule, so we had Plan 2. And even though we have Plan 2, every reporting period, we still put in the actuals. And Plan 2 said in April we're going to have 350, and the truth is actually in Plan 2 we only had 300. So in Plan 2 we're still 50 behind, and Plan 2 said we're going to have 600 in May, and we only have 400 in May, so we're 200 design, and theoretically we should have had Plan 3, a cost impact. So Plan 2 said the schedule is going to be here, and now we have an impact, and maybe the schedule will be out here. So even though we had Plan 2, we still do the actuals to see how well are we meeting Plan 2. So again, what I'm saying, this gives you, tracks your ability and your progress in the design phase. Okay, we're going to talk about some module development and spend a few moments. I want to leave about 10 minutes at the end for questions. Now this looks complicated, but again, this is in the code, in the module development or the coding phase, where you're doing the coding, where you're designing your modules, and you're coding and testing your modules, and you're integrating your modules. So let's say, as an example, there are 800 modules in this program, and for each of these, and we're dividing development into designing the modules, coding and testing the modules, and integrating the modules, and when you're finished designing, coding, testing, and integrating, you're finished and ready for system test. So for each of these three parts of development, we do the same thing. We have planned and actuals. In coding and testing, we say we're going to be able to code all the 800 modules with this productivity level, saying in August we're going to be finished. And then we have the actuals, and then in the integrating, we're going to be able to integrate 800 modules here, and this is the actuals, and let's say this is where we are now. So again, what we're doing, the same thing. We're saying here is the planned schedule for designing 800 modules. Here is the planned schedule for coding and testing 800 modules. And here is the planned schedule for integrating the 800 modules. And then there's the actuals. Let's take a look. Let's take a look. We're in March. In March, we had planned to be finished successfully designing 350 modules. And yet, actually, we only designed 250 modules. So in March, let's keep this in. We're 100 modules behind our plan. And what we're saying is, in April, we were going to start coding. We can start coding on the earlier modules that we've already designed. And what we're saying is this is the planned schedule. And in May, we expect to have 150 modules coded and tested. And in June, we're supposed to have 300 modules coded and tested, and we only have 200 modules coded and tested. So where are we in June? In June, we're 100 modules behind in coding and testing. And in June, we're probably about 100 modules behind in successfully designed. So one would say, in June, we should be alerting management the potential problem, and maybe coming off with a course schedule impact. Because in June, we're behind 100 modules, and we're behind 100 modules in design. So once we get to June, it seems with the use of these progress measurements, we can see a very serious potential problem. And as an example, and then again also we see the potential problem here. So again, what this module development progress measurement tracks the ability to stay on schedule in developing, designing, coding, testing, integrating the modules before you're ready to go into system test. And it seems like in May already, there's a whole lot of potential problems, which means you will not get the system test in time, or if you get the system test, you may not even be ready to code and test or to integrate all your modules. So again, this is an example, and some people, rather than have, code, test, and integrate, you may have one line for each. So then you have coding again. But basically, we're talking about the planned schedule and the actual schedule. And the planned schedule is basically a productivity curve. How fast can you code and unit test 800 modules? And in the beginning, you have to have some estimate, or else how do you know you're going to be meeting your schedule of being finished in December to go right into system test? So again, this is a unique metric. Each measurement or each metric only measures one thing, and when you put all these measurements together, you get a rounded view of where you are. And in many organizations that use measurements, every reporting period, whether it's weekly, bi-weekly, or monthly, the SQA team or some team reports all the measurements to management and staff. So you get a good example, and people look at the measurements and say, how, as an example, the software size is increasing, the staffing is decreasing, the requirements are changing, we're behind in coding and unit test by not just a whole lot. Here we know objectively we're behind 100 here, and we're behind 100 design. How can we meet this schedule of being finished with this here with all these problems? So all the measurements are briefed. Okay, that's about it for now. Just, by the way, a 1-hour overview of a seminar and a tutorial that I'll be giving at the conference. That's a whole day, and we'll be talking about close to a dozen to a dozen and a half measurements. Let me ask if there are any questions.
Thank you, Al, for your time today, and thank you to everyone for joining us for today's webinar sponsored by IIST, the leaders in education-based certifications and training. For more information on how IIST can help you or your organization, please visit www.iist.org. You can follow IIST on Facebook, Twitter, LinkedIn, and YouTube to find out more information on IIST news, events, and promotions. Thank you all again for joining us today, and have a great day.